Okay, so this presentation is last Friday. I was trying to think of a way to dualize the data from Americ's data. And so, but not just for that. Another reason is also Klee wants to look at a simple model of in the Penrose tiling, and then like those different ways of connecting those edges, and then you wanted to check a certain kind of ordering thing. So that's related to this. That's okay. So,
like in other words, we want to get a bunch of Penrose tilings and invent an algorithm for what would evolve the ordering from a random ordering to some ordered ordering where we can see quasi-particles, but we want rules and syntactical freedom.
Right. So how the order?
Well, that makes it look 3D.
Yeah. Okay. So this is a projection of a Z5, and you can see all 31 points.
Just a 5 cube.
2 points. Yeah. 5 cube. And so then there are a variety of different ways of actually select the tiles to make the Penrose tiling, and then we'll try to start the order. So this is a one way. Okay,
so that's like the possibility space for a very small section of the Penrose tiling.
Right. So that is a one way, and then I'll just draw in the ribbons on it, so you can see, because both in Amaral's project and also I think in what I have been always attracted to, the interactions of the ribbons. So that's why I always kind of consider this as a set of ribbons, and then how they interact with each other, like, because two ribbons always cross each other at a tile. So each tile or each Fibonacci letter there represent a node. I call this node if these are ribbons, and then when they cross, I call it a node.
Node.
Oh yeah, a node. Thank you. Okay, so then I also number them, and this purple would be number 1, and then this is number 2, number 3, number 4, the yellow, and then the blue is number 5. So in this like a very small set, we only see for each ribbon direction that we only see one. In Penrose tiling, you would see kind of other purple as well, purple ribbons. They're parallel. By parallel, I mean, if you take an average kind of a line of averaging this wiggly ribbon, a straight line, so they will be parallel. And the distance between them actually are equal. Okay, so we have seen that before because I showed it before. So now to make everything simple, so just like one ribbon from each set, and then and there are 10 nodes. Okay, you see these two intersect at the short, and we call this big one long, and this is a short. Okay, so for here, for example, then I can develop the code. So number 1 and number 5 intersect at an S, and number 1 and 3 intersect at a L, and then number 1 and 4 is a L, and number 1 and 2 is an S. So you see S, L, L, S, S, L, L, S, right? Yeah. So the tile type is the small one, the thin one, I just call it the S. And the fat one, I call it L, right? So if you follow this, it's a S, L, L, S. And similarly for this red one, so that's a S, L, L, S. And then this S is just not just any S, it is not the 2 intersecting with 3. Okay, so that's why I said 2, 3, S. So you know the labeling, right? So it's a ribbon 2 intersect the ribbon 3, and at the node that is S node. Okay. Okay, so now we understand all the labeling here, and then let's see if there is a face-on flip, or if there is other ways of tiling the space. What would the ribbon change? How would the nodes change?
Will I be able to comment on the over-under? using this view graph?
After, please,
Okay.
because you would have an opportunity for that for sure. Okay, so you see before and after? Did you notice the face-on flip? Right, it's just the flip here. Okay, so now let's look at the, again these kind of labeling. So I did the same thing. There is no change here. There is some change here, and then I wanted to put them together so we can see. So you see, as before, when we have this, the 2 and 3 intersect at a short, right, which is right here. That's before the flip. And after the flip, they are intersecting here, right? The node changes position from this thin rhomb until this thin rhomb, but it's still an S. Since before, the ribbon 2 and ribbon 3 intersect at the S node. And after, the ribbon 2 and the ribbon 3 also intersect the S node. But what's changed is, originally, the 2 and 5 intersected the fat rhomb here, right? And then so if you follow this, it's gonna be S. So this thin, and then a fat and thin. But here, in this case, which is this one, and so it's going to be a fat and thin and fat and thin, right? So it's actually the switching these two.
So it represents a phase-on flip there, and then you do the analysis with ribbons, and you get this listing.
Yes.
And so you get a Fibonacci word, an L and S, along each ribbon.
Yeah, this is S and L, and here's L and S, but you can see the 2 and 3 always intersect here at the S, and here, the ribbon 2 and ribbon 3 still intersect at the same node, same type of node. Only the ordering that change. Can you understand? So it's before 2 and 3 intersect at the S, and after the 2 and then 3 intersect at the S. And then it's before, it's after this, we come to this one, which means the 2 and the blue intersect the fat. Now it's the red and the blue, the 2 and the 5 actually intersect before this. So it's like a switching of the order. It's like these two literally just switched.
This is cool.
So what I wanted to emphasize is, when ribbon 2 and then 3 intersect and then S, it's always going to be S. You're never going to be change this one. This will never change. What changes is, like for example, you have all these ribbons here and then they're intersecting, and then there is almost like you pinch them together and they become an L, or you pinch them together as an S. But this never changes. What changes is this one and this one, these two nodes all of a sudden shifted the order, along certain kind of ribbon, because, we're talking about the ribbon 2, so it's like now that instead of intersecting blue first, here now instead of intersecting with green first, now intersected with blue. So it's like this, if this is 2, and then here they intersected the 5, here they intersected 3, somehow you put this down and you put this up. So there is an order change, and that's all. Only the order changes and the letter doesn't change. If you look at a matrix of, these 5 by 5, and so, 2 and 3 would be an S, and always going to be S. So what America gave me a matrix that I'm going to show you later, that actually he's changing literally these nodes. He's like originally the 2, 3 intersect at S, and later on he put it into an L, which is never going to change as a legal face-on flip. That's never going to happen. So that's why there is no way to dualize that.
So let me add something here. So there are 12 possible ways to legally tile this possibility space. So we have 31 points, and your 12 ways can be defined as binary actions on the 31 points, where you must, in each of the 12 legal frames, select 16 points to be on, and you must select 15 points always to be off. And those combinatorics that are legal are the 12 possible ways to tile this decagon, which are legal. So what you just helped me to realize is that, well, you guys have all read the Code Theoretic Thermodynamics paper, and you hear me talking about time domain quasicrystals and spatial quasicrystals. So here, vertically, we have a time domain quasicrystal. So what Fang just made me realize is that within the ordering, if I order it completely randomly, the time domain quasicrystal will definitely not follow the rules for short, long, long, short. It won't obey those rules. And so perhaps nature seeks to self-organize into a time domain quasicrystal, right? Because we know that when we disorder it over the time domain such that it doesn't follow the Fibonacci sequence rules, that it will behave very chaotically and noisy. You will not have coherent quasi-particle patterns in your animation. So maybe we should be advancing the thinking on what determines the time domain to evolve towards following the rule vertically for your Fibonacci rules.
Yeah, so I just wanted to show them again so you can see the wiggle. It's really, notice this node, this node, this node, these three. See? It just literally that node changes here, and these two changes, they're just changing orders, right? So it's literally a shift, but these, it's almost like these together changed in there. See? There's a shift, but these two always intersect at the fat. So, oh, actually, it's a blue, and then it shifted here. Yeah, and then this one is shifted here, and this guy just shifted there.
Okay. May I also explain some stuff on this drawing, but I want to do this after you explain us the over-under.
Yeah. Okay.
This is cool, Fang. With these ribbons, it's always given me a good visual intuition for waves, because when you're just looking at angles, it's hard to visualize waves, but when you sort of smooth things out, you see everything is this waviness interaction.
Yeah, so just so I don't miss key points, so here are 5 lines are indexed 0 here, yeah, because they're all indexed. And there is only 1 line for each family. The letter of label of each node never change. For example, the nodes of blue line, purple line 0 is always S. This kind of fits and flips, I can track the order and give an algorithm on the interactions and influences on the change of order of nodes in the ribbons. Okay, so then when an order change involving line A, B, and C, okay, yeah, these are the coding part that I kind of don't want to talk so much about it. So it's talking about how do I track the order. If there is any change, there is certain ways that I can track always, if I know there's some change here, then I can keep tracking, the change in order. And that's what kind of like, if America does it this way, then he can have a dynamic kind of interaction.
But this shape is not one of the 12.
No, this is not one of the 12.
Yeah.
This is another kind of face on flip. See, this is another face on flip, but it is a generalized Penrose tiling.
It's not part of the ordinary Penrose rules.
It's not the true Penrose tiling.
Okay, so we can have a little more than 12 in this case.
Mm-hmm.
If we allow that. But what I'm looking for is to Occam's razor, Fang, to see if we can use defects in the time domain and use every frozen state as an ideal rule-following quasicrystal. And then the system self-corrects and evolves towards fewer defects over the time domain, the ordering.
So I have something here, but it's related to, you know, how when two ribbons intersect, which is right here, and how they trade position to be the perfect one. I was noticing like these ribbons take turns to be perfect. So when this guy is perfect, the next time the other one, like if two ribbons intersect, one is completely perfect, another one intersecting is not. But when this guy flips to the other side, then this one starts to be a so two ribbons intersect. This one is perfect and this one is almost perfect, but here is not because it only allows one to be perfect. So but when they flip and this one becomes perfect and this one has a little kind of defect there. Oh yeah, this one and that one. Okay, now I got it. So you see this guy is not perfect because of this here, right? This ribbon is everywhere is perfect except here. But this guy is a perfect ribbon, perfect Fibonacci chain. But after the flip, this one becomes perfect and this one is not. You see what I'm saying?
I see. So usually for a good ribbon, the green ribbon here, the smaller tiles, they come in pairs, and that's one short segment.
Yes.
And two big tiles constitute a long segment. But
yes, so you can follow it all along, and then you can see it's perfect everywhere except it's perfect everywhere. But if you look at this guy, it's also perfect everywhere other than when it intersects with another one, right? When it intersects with this guy. But notice after the flip, and this guy become perfect and this guy is not. So there is certain kind of a code there that I noticed. Anyway, but
these are generalized Penrose.
That's a true Penrose tiling. Anyway, so I developed certain kind of rules to be able to to be able to explain that. So how exactly they trade in really interesting ways. Like they exactly trade position right here. Like the red and the green are exactly, so you see this and this, they look the same. And then they're trading positions, actually. So that's just that part, and I haven't finished with, I don't know if it's still interesting to talk about Amric's stuff, but...
And then I want to talk about OverUnder.
But I want the kind of them to know because especially Marcelo, so what Amric gives is like this. So for example, he also used the ribbons, right? So each ribbon family, he gives 3 ribbons. So this is the direction 1, he gives A, B, C. For example, 3 ribbons in that direction, 3 ribbons in the second direction. So in each direction, he gives 3 ribbons. So the ribbons are gonna intersect with each other, right? But it does not intersect with each other in the same family because they're the same orientation, so they don't cross. So but the ribbons of a different orientation they always cross, and then when they cross, there is a tile there that can be called either L or S. Okay, so for example, the 1A and 2A they intersect at L. And then 1A and 2B intersect at S. So you can see like you can have all these letters here. So what his code does is he take, for example, this as a chain, that as a chain, and then he started to build this as one fab, like kind of like a defected one-dimensional crystal, quasicrystal, whatever. So then he uses empire and all those things to in 1D method, right? He uses the 1D method to relax the energy, so this will be as close to a Fibonacci chain as possible. And then so all of them needed to be as close as a Fibonacci chain as possible. And then he calculated the sum of the energy. And if the energy is a little bit lower, then he picked that state. So what's gonna happen is, for example, the 2A and 3C intersect at L, but in his case, he would change this to S. Instead of L, he changed it to S. So this is not this does not happen in the fix and flip. Like this is a completely different thing. So that's why I can't track his order and I can't dualize it. So he's gonna have this higher dimensional lattice there, and then with these changing of these nodes, which is really not
like a little artificial. He has a step that's not based on geometric first principles.
It does not based on like in Penrose tiling that doesn't happen.
Yeah,
that won't happen.
Right.
So it's a different thing. I don't know how he dualized it, but I'm just kind of like explain so you be clear on what I was talking about that day when I say, this is not really any kind of a legal fix and flip.
Yeah, what he said is that you can, because he is using a random generator or something, there are some probability to choose.
A random number generator?
But you can maybe change to...
No, but that's not matter because for legal fix and flip, the 2A and 4B always intersect at C, never change. What changes is the order, like I said here. Okay, so what changes is, instead of that 2A, 2B, 2C, 2, like that, what's gonna change is after 2A, you have 2A, 3A, and 2B, and 4A, like different orders. Like you could move 5A before 5B, before 3B or something like this kind of order change. But when the L changes, it has to move this guy together with him. So then in this matrix that we have, the 5A and then 2A always gonna be L. What's changing is the ordering of this thing. So which is in his case, he never tracked the order change, the node change. He's leaving that node there and just change that node to an S or L.
He's evolving he's evolving in his algorithm the legality of each frozen frame, whereas in Fang and my preferred approach is we deal with order.
No, not even that, Klee. Mm-hmm. Not even that, because from his frame 1 to frame 2. It's not even too legal.
Right. But at
at
the end, right, as he approaches the end of the evolution of his algorithm, the frozen states get improved in terms of their legality compared to the beginning of the algorithm.
I don't know what's changing. What is changed is this hypothetical thing that is not even connected to Penrose tiling.
Okay.
Yeah, because he didn't even start with the Penrose tiling, and it's not ending with the Penrose tiling, and it's not following any kind of rules in Penrose tiling.
Yeah. Oh, may I explain how we could go to some geometrical stuff?
Yeah.
Will be 5 minutes maybe. I need just the slides that we had before. So this encoding could be a little simplified. Just by seeing this as the vector for 1, SLLS, for 1, SLLS. This is the vector 2, LS, LS,
yeah.
LS, LS, 3, 4, 5. So you have a matrix just of 5 times 4. 4 is the length of the subchain inside of this decagon. Then the possibility for this whole matrix, if it stays Penrose tiling, is, as Klee has said, it's 10, which is 12, 10 rotation of this one,
mm-hmm.
and the 2 stars.
Yes.
So you have only 12 possibilities for this matrix 5 by 4, which is encoding one part of the Penrose tile. And the part is a decagonal part. Mm-hmm. So if you try to apply something like Amaral has done, a method of relaxation, but globally to each decagon in the Penrose tile, it may work. But then you have something which is complicated. When some tiles are belonging to 2 different decagons, you have to take into account that when you will modify the matrix, it will modify also the other matrix. So it's a complex interaction, complex to implement, but easy to describe. So I'm sure that with such a system, his way of computing an Hamiltonian converging to Fibonacci word by using the empire, the 1D empire, will be able to describe quasicrystal with or without defect.
Yeah, but really I'm just saying you can't really eliminate those kind of the 2-5, those 2-3, those kind of intersections, because that's what tracks the order.
Oh yes, but I'm making this globally for this.
I know for this one single thing, you can kind of do that, but when you have 5-3 or 5-7, those kind of things, you have to have that. Otherwise, the order because there are many 3-5s.
We don't have to deal with order. The order was interesting so you was able to demonstrate that his method by changing one value cannot work. So right. It was very clear because of the order. But the method I propose is more global, is at the scale of each decagon, and automatically it will work. It's just that it's difficult to implement because you have to encode all the intersection of different decagon in the patches. It's very complicated.
And also that's too local to me.
There needs to be a global cut
No, the global stuff will be the way of evolving 4x4 the braids. But maybe it's maybe it's too local. But anyway, it will work better than what was done. But it's more complicated to implement. And
what?
The on-off or the...
Oh, the over-under.
I want to say a comment about the over-under.
Over-under. You want which slides you want?
I'll find it.
One more comment. I think this order is more like you want to evolve one state to other state. So it's more like if the Hamiltonian works and you get a Hamiltonian for a quasicrystal, you could use to evolve some state to other state. Then you have disordering.
Yeah,
but the Hamiltonian is just a relaxation
to... His Hamiltonian does not associated to a quasicrystal and or legal changes in a quasicrystal the way that he built now. Because there is no way to convert his matrix to a quasicrystal in any way.
I mean, his thinking, his approach evolved from his one-dimensional exercise, and that, as you remember, was to evolve an object which is not a quasicrystal into eventually an object in 1D which is a quasicrystal. So the whole premise of his kind of approach is inspired by an algorithm using empires and using locking, which is logical. I want both of those two things, locking and empires, but I want it to evolve a set of ideal quasicrystals that are disordered and therefore represent a high entropic, noisy animation, and then to have an algorithm using locking and using empires that evolves the ordering parameter into something that has different magnitudes of order quality.
Yeah, you want the work because he has you start anything and it evolves to the Fibonacci chain. So you have the Hamiltonian for the Fibonacci chain.
Yeah, that's because it's just 1D, so it's okay to do it, but in 2D, because 2D does not work as simple as that, because it's not like it's not even a network of one chain and another chain. It's a dimension of like he said 5 times n and then times 5 times n. So it's a super matrix almost. So in that way,
I'm just saying that if it works in some way, like U1D, you can use that Hamiltonian to calculate evolution of legal states.
Okay.
It doesn't expand to 2D. I don't think so, because it works in 1D. It's very trivial. When you go to 2D and then the method no longer, I don't think it'll work anymore.
In the method I described, it can be extended to the Penrose
So it's
tiling, but not in the method that Amaral has the.
I proposed a method that can work exactly like how it works in 1D. But it's not the way that he's building it right now. I don't think that's gonna work. But anyway, because there is no way even to prove what he eventually got would be a quasicrystal.
Because you want to calculate entropy. So in 1D you can calculate because you have the Hamiltonian, so you have the partition function, then you can work. So we always expect that the extension to 2D could work too. So maybe
more accurate.
There are different ways. There are other ways of building it.
I mean, more accurately, what we want to create a simulation algorithm that non-deterministically reduces entropy, and that is simply stated as this would be ideal entropy. This is ideal entropy because vertically over the time domain, these are all ideally ordered Fibonacci chains vertically, but we could order them a large set perfectly randomly, and that would beautifully model a very high entropy state. So anyway, but let me switch.
OverUnder, yes.
Yeah, OverUnder. So this is a beautiful diagram because by making this diagram, Fang gives us the illusion of depth. So imagine I am a projector here in 3D, and this is my window. So my window is really what I can hold within my arms. And as I move through my projection space, what I do is here I capture things that are closer to me and farther from me, to my boundaries. So my window has a boundary on both sides, and then as I begin to capture points within my window, I can ask, or I can imagine here there's an abstract projection screen, and I can ask, well, in my window, are there different distances between the points in my higher dimensional space relative to my projective space, or relative to some boundary of my window? So here clearly we have an over-under idea, where we can say relative to this or to this, this is over or under or before or after or further or closer. I'm trying to relate this to anyons. So anyons are very important because they do such a good job of modeling the quantum mechanical probabilities of things, and as an abstract model in 2D, they absolutely have an over-under quality. And you can get this here as an analogy in the Penrose tiling. On the plane, there is no notion naturally on the plane of over and under. You have to artificially invent that. And in some sense, anyons are an artificial invention, a very helpful mathematical tool where you artificially decide on the plane, oh, okay, I am going to say that this line is over this other line, and then you just label it that way. But in a Penrose tiling, I can ask myself, well, hey, this point and this point, which one is over or under the other one from first principles in the projection window in the higher dimensional space? And I can have an answer, and then I can label it over, under, or closer or further in the plane, and have it be less artificial in terms of my abstraction. So the interesting thing is in the QSN, we actually have over-under. We have real braid structures. So there, it's not abstract, it's literal, geometric. But those over-under objects also come from actual over-under relationships to those points that form the braid have another home, right? Each of those points has another home in the higher dimensional space relative to their closeness or distance or over/under relative to the projection window boundary or to the projective subspace. So I don't know how helpful that is. It's just an observation because I keep trying to imagine some intuitions about how Fibonacci anyons are going to be conceptualized in the QSN. How are we going to use them, and can we invent a completely new type of analog to Fibonacci anyons, where maybe we don't use anyonic theory, maybe we use braid theory, but they're Fibonacci braids or something, and we steal some ideas from anyon theory in the formalism.
So just for this, yes, I believe that another image is, for example, this image is better because, in fact, what is interesting is
stand further because you're blocking them.
Is the intersections of the ribbon. So necessarily to draw it, Fang has made one. The red is over, the green is under. And so the question that Klee asks is from where it comes. So, and the first answer is we can see this as a two-dimensional projection of a three-dimensional object, which is a rhombic triacontohedron. And so each of these endpoints of the ribbons have to be seen in 3 dimensions. And then there is a path in 3 dimensions, and there is over/under.
Yes.
After that, this 3 dimension itself is a projection of the 5 dimension.
Yeah.
So maybe there is different possibility, but yes, I can see
something
we
there,
can go to this direction.
Some little ideas, but Fang helps me a couple years ago by her being interested in ribbons. Like she was interested in ribbons before I was, and this is sometimes she draws the ribbons with the entire tile, sometimes she puts smooth arcs around, through the centroids of the tiles. But anyway, it gives you the notion that when it's dynamical, it's a wave-like space of interactions. The last thing is kind of very unrelated to what I just said. Is there many images of this?
Yes. I was planning on doing something there, but...
So, well, this is not the best image to point something out to you, but I'll do it anyway. Here is an object which is completely analogous to the 20 group. In other words, the density, so there are only 2 types of decagons possible in the Penrose tiling. There is the star decagon, and there is this other decagon right here, which is called the cartwheel decagon. This one has 10 legal orientations or rotations, and this one, depending on whether you're talking about the Penrose tiling or the generalized Penrose tiling, can have 2 or 1. I mean, in the Penrose tiling, so here we have 1 and here we have the other. So anyway, if you consider the QSN and you look at the density of 20 groups in the compound quasicrystal relative to the density in the 3 space, relative to the density of the area of these star decagons in the 2 space, it's a similar concept. It's a similar level of density. I'm not saying it's very close, but it's a very interesting thing because there should be tiles in the compound quasicrystal that are a little more ugly. That is, if you like symmetry, if you like rotational symmetry, you're going to have the 20 groups, which have a very beautiful rotational symmetry. And then, as we saw today, we have these 12 groups, which are a bit ugly in terms of their rotational symmetry. They're similar to the cartwheel tile. And so the idea is that what if these 20 groups, let me represent these star ones, these are 20 groups. So what if 20 groups are fermions? And the fermions come in 2 patterns that have not-like qualities. They go through a Hamiltonian circuit over n frames, and one of the fundamental patterns is an electron, and the other fundamental pattern made of 20 groups is a quark. Or perhaps the fundamental pattern is not a quark, perhaps it is an entire nucleon. since we've never observed a quark separately. So you have a big complicated nucleon structure, like a proton, and then you have this made of 20 groups that take a winding path that closes, maybe. And then you have another pattern that's an electron, and it has a closed, simpler, smaller knot. And because I want you to be impressed by the density of the star decagons, so that if I suggest to you that I want to make a 2D reality and I want to use these as my fermion patterns, and I want a density of fermions in my 2D world that's similar to the density of electrons and quarks in our universe in 3 space. Well, the first thing you should say is, well, Klee, that's ridiculous, because the density, the known density, the average density of the electrons in the universe is fantastically smaller than the density of 20 groups in the compound quasicrystal, or the density of star decagons here. And so we actually must have a super high density fermionic appearance. We have to have this because when Paul Dirac invented his deductive conclusion that the Dirac sea is real, if you follow the deduction of quantum mechanics, we didn't know when he first conjectured this that there would be physical evidence for the Dirac sea. But in the 1980s, we had technology that began to do some experimental evidence, strong experimental evidence that the Dirac sea is not just a mathematical abstraction of Paul Dirac, that it is really going on. There is really the appearance of an electron for a fleeting moment, perhaps one Planck moment, and then it's gone. And then another one appears here, and it's conserved. So that in the Dirac sea, the average density, the average quantity of electrons in the Dirac sea is conserved. It's just that they're rapidly appearing and disappearing at very close distances. So if you take the Penrose tiling and you color these red, only the stars red, and you take 100 frames of the legal Penrose tiling of a very small one like this, and you allow a random number generator to organize each of those legal frames, and you pay attention to the red ones. And if you play that at 24 frames per second, you will see something incredibly noisy. You will see all virtual quasi-particles that appear for one frame and then they're gone. You can't see where they go next because it's as though they're randomly appearing and disappearing. And then you take your 100 frames and you slowly evolve the ordering quality over the time domain, such that on Fang's table, you begin to slowly evolve the vertical ordering to ideal Fibonacci chain patterns that follow the rules. And that as it slowly evolves with however you build your algorithm to do that, then all of a sudden in your animation, which would only last 4 seconds at 24 frames per second, you play it again for another 4 seconds. And at the end of the evolution of this algorithm, you would see an ideally ordered state where only some of these star decagons can be in a given frame a position for a non-virtual particle. Because you must realize it's impossible to have every one of the 20 groups, no matter how you order it, be a coherent quasi-particle illusionary pattern. There's too many of them. Most of them, even at the ideal order, must be sacrificed to participate in the Dirac sea, and then only some of them in each frame could participate in the maximally low entropy patterns of where you get 99.99% virtual 20 groups that are noisy, and then a very small percentage that are coherent, orderly quasi-particle animations.